Okay. So we're starting the seminar for this week. I have the honor to have the Professor Charles Horowitz from Indiana University in Bloomington. He got his PhD from Stanford and then made a postdoc research visit on Bohr Institute. And he will talk about the PREX collaborative experiment and for neutron density experiment and neutron stars. So thank you, Professor, for giving us this talk today.
Great. So let's go over here. Whoops. Let's try and go here. There, that looks better. Okay, so thanks for the chance to visit and talk, and please, if you have questions, interrupt. There's stuff at the end, but I'll cut it if we don't get there. And so the one thing I should not cut is a student, Brendan Reed, worked with me a lot on the interpretation of the PREX and CREX experiments, which I'll talk about. So let me mention Brendan Reed's name if I don't get to the full credits at the end. Okay, so I'm going to talk about two parity violating electron scattering experiments which measure neutron densities. So I'll give you a little bit of an introduction. We'll talk about neutron densities and we'll talk about nuclear density. Where did 0.16 nucleons per cubic Fermi come from? So the PREX experiment measures the neutron skin in lead. This is a way of measuring the equation of state, measuring the pressure of neutron-rich matter, and I'll motivate that. And then I'll compare the pressure here from this experiment in the lab with X-ray and gravitational wave observations of neutron stars. And then finally, we have a second experiment measuring the neutron density of calcium-48. Calcium-48 is another neutron-rich closed shell nucleus, and this has implications for nuclear structure. So we'll get to that. Okay, so the important thing is to complain and interrupt. And I thought one way to start is let's start in the 1980s. We have a standard model of nuclear physics, and just to get oriented, we're gonna build all the nuclei. You start from phenomenological two nucleon potentials. So the potential between two nucleons is fit to scattering phase shifts. So there's a lot of complicated scattering data, and the result is this complicated, strong spin and angular momentum dependent with this tensor force and whatever. We have this two nucleon potential, and it's fit to two nucleon scattering. So that's phenomenological. And if you like, what defines the model is three nucleon forces are assumed to be small. And motivation at the time was three nucleon forces are pretty complicated, so it's a lot simpler if we ignore them. And also, this two nucleon alone sort of worked. So the model sort of worked, and this is what defined it. So if you only have two nucleon forces, phenomenological, you then just solve the many-body Schrodinger equation as well as you can, and it's complicated because the force is complicated, but that defines the model. Great. In hindsight, and I'm not sure we fully appreciated how much was broken at the time, Ben Day at Argonne National Laboratory broke the standard model of nuclear physics already in 1981. He did extraordinary calculations for the binding energy of nuclear matter, and showed that nuclear matter alone, with only 2 nucleon forces, saturated at too high a density. So if you just had 2 nucleon forces with no 3 nucleon forces, you'd get nuclear density wrong. So you needed 3 nucleon forces. And that turned out to be revolutionary. So let me say, you need important 3 nucleon interactions to get nuclear saturation right, to get the density in the center of nuclei. We'll come back to that. But it's hard to determine these 3 nucleon forces from few nucleons out. So the idea that the force is phenomenological from nucleon scattering is now on thin ice. And that's the thing that really was broken. And of course, our alternative is chiral effective filtering. So we don't use phenomenological 2 nucleon forces, although it can look pretty similar. This chiral effective field theory expands 2 nucleon, 3 nucleon, 4 nucleon interactions in powers of the momentum over a chiral scale. So chiral effective field theory can predict the 2 nucleon and 3 nucleon forces. So you gain one thing and you lose one thing. So what you gain is you can predict these guys. They have some constants which you can fit to data. What you lose is when this chiral expansion breaks down, you're lost. So the old phenomenological model, you could calculate the binding energy in the equation of state of a neutron star up to arbitrarily high density, but we can't do that anymore. So the modern standard model of nuclear physics is less predictive. Okay.
Is the nuclear interaction from parallel effective theory the same as the phenomenological model?
Not really, and that showed a lot of the ambiguities. If the 3 nucleon force phenomenologically was fit to reproduce the binding energy of helium-3 and the tritron or something like that, then it did it, and the chiral could also do it. But the 3 nucleon force looks a lot different in general. So there were important ambiguities in the 3 nucleon force. And you couldn't figure out those ambiguities if looking at the binding energy of light nuclei or scattering data. Okay, this is a long introduction to remind us that nuclear saturation, nuclear density is really crucial. It's fundamental to nuclear structure. Nuclei. Okay. What we mean by nuclear saturation, there's a minimum in the energy versus density curve for infinite nuclear matter, and that minimum, we think, occurs around 0.16 nucleons per cubic Fermi. So that's why we call this number nuclear density. That number has never been directly observed. So we'll keep track of that for a second. Another way to say nuclear saturation is the interior baryon density of a heavy nucleus should be more or less flat, should it's approximately constant as a function of R in the interior of a heavy nucleus. And that constant is more or less independent of the mass number of the nucleus. Okay, so that's another way to say nuclear saturation. And this guy is much closer to experiment, so I want to use that. Okay. The problem is we've never observed this very well. Here are charge densities. So we can model independently, very accurately measure the charge density of various nuclei. And helium's a really light nucleus. calcium, and so on. Lead, I'll talk about a bunch. Okay, so those are the charge densities, and they don't really saturate very well. So this isn't so much of a constant. The best thing you could say is the interior of lead is indeed the charge density in lead is pretty flat. So that looks like nuclear saturation. 0.06 is something like that, nucleons per cubic Fermi. That's the charge density of lead, but that's not nuclear density. We thought nuclear density was 0.16. Okay, so just looking at the protons and the charge density, we're missing more than half. So we want to measure all this. We want to measure where the neutrons are, and we want to see to really check experimentally this idea about nuclear saturation. We have to locate the neutrons. Okay, so the PREX experiment uses parity violation to locate the neutrons. So the weak interactions, the standard model, the Z boson couples to the weak charge, just like the photon couples to the electromagnetic charge. The weak charge of the proton happens to be small. Sine squared theta W is this weak mixing angle, the Weinberg-Salam angle. The weak charge of a neutron is big. So if you can isolate the weak interactions, we can see where the neutrons are. So we have this very clean but very difficult to use probe of the neutrons. And parity violation is the way to isolate the weak interactions. And the parity violating observable is this asymmetry, the cross-section for scattering positive helicity minus the cross-section for scattering negative helicity electrons. So if you reflect a positive helicity electron in the mirror, it's negative. So this observable violates parity. And it's the weak interaction. It's about a part per million. We'll get to that in a second. In the Born approximation, it's the interference of a weak amplitude, order G Fermi is the Fermi constant of the weak interactions, over the electromagnetic. So the electromagnetic has alpha, the fine structure constant, hidden under there. The weak form factor, this is the Fourier transform of the weak charge density, and the weak charge density is essentially the neutron density. So that's how we can model independently locate where the neutrons are in a nucleus. In principle, if we measured this parity violation as a function of momentum transfer, we could map out the neutrons. This is the charge form factor. This is where the protons are, and we already know that. Okay, so that's the idea, and it's hard because it's only a part per million, this parity violating asymmetry. The weak interactions are weak.
What's the Q-squared dependence of QW?
So this here, the weak charge of lead has radiative correction, so it's not strictly conserved. But the short answer to your question is it's the low Q-squared limit.
It's what?
The low Q-squared limit.
It's a low Q-squared.
So it's something like asking, what's the Q-squared dependence of alpha?
Oh, that far down, okay. So
It's basically
low
this is the,
Q-squared compared to the mass of the boson, the Z boson or something like
Yes.
that. Okay.
Yeah.
So that is low, for
Yeah.
sure.
so it's a number approximately equal to the number of neutrons. It's a little less because the protons have opposite charge. And so you have something for lead, it's about 118 rather than 126. So this is 118, and of course 82 is charge. So that ratio for a neutron-rich nucleus is a little bigger than 1. And I should probably say atomic parity violation. So this beautiful cesium experiment actually measures the weak charge of cesium. Okay, great. So I just want to keep track. We're going to be measuring the weak form factor, which is the Fourier transform. J0 is just a spherical Bessel function. So this is the Fourier transform of the weak charge density. The weak charge density is the neutron density, and you can fold it with the single nucleon form factor. This is the weak form factor of the neutron, and it's about the same size as the charge form factor of the proton. This is the weak form factor of the proton. This is small because the weak charge of the proton is so small. So the weak density is the neutron density folded with the size of a single nucleon. The charge density is the proton density folded with the electric form factor of the proton. Okay, so we'll talk about the neutron RMS radius, which is the radius of the point neutron density. And then the weak radius includes a little bit from the size of the single nucleon. And we'll talk about skins. So the neutron minus the proton, or almost equivalently, the weak radius minus the charge radius. So this is the observable, and these are the point neutron and point proton.
So R sub charge includes the finite proton size
Yes.
in it. So that's what would be directly measured experimentally.
Yeah. So for lead,
No Q squared.
the charge radius of lead is known very accurately. It's 5.50 Fermis. And it's a little bit bigger than it might be 5.45 Fermis for the proton radius. Great. Okay, and here's just some pictures to keep track of these densities. So this is an old relativistic mean field model of lead. The dashed red is the point proton density. So the area under that is 82, the 82 protons. If you fold with the form factor of the proton, you get the solid red line. So that's the model charge density. And that's close to the experiment. This bump in the middle is a little bigger than experiment, but otherwise that it's pretty close. And then we're interested in the neutrons. So the black dash is the neutron density. The area under that is 126 neutrons for lead 208. And then this is the weak charge density. So the distance from here down to there, that's the small charge, the weak charge of the proton. Okay, so if you're measuring parity violation, this weak charge density is the observable, and this guy is very closely related to the neutron density. So this PREX experiment, the single low Q squared measurement of the parity violating asymmetry, we'll talk about seeing how far the neutrons stick out compared to the protons.
So R sub CH was the root mean square radius of the solid red.
That's right.
R sub W is the root mean square radius of solid black?
Yes.
Okay.
Yes. So the solid curves are the observables. The dash curves are the point nucleon.
And the arrows are pointing to something. What?
Oh, the arrows are tricking your eye. And I'm just saying, we're measuring the size of the black curve. And since we already knew the size of the red curve, we knew the charge radius, that we're seeing how much the black curve sticks out compared to the red.
But that's not, that point is not necessarily indicating the RMS radius. That's just some size difference at a fixed density.
Yeah, so that's just a way of showing on the picture that the weak radius is bigger than the charge radius. Good. So I actually have the experimental figure that we published does this better. So I'll show you a better figure. Okay, doing the experiment involves essentially all of Jefferson Laboratory. Intense polarized electron source, you accelerate the electrons to 1 GeV, direct them on a target. It's a thick, 0.5 millimeter thick lead foil target. It's enriched in lead-208. So you have this thick lead foil. It's sandwiched between two thin diamond foils. The diamond has a tremendous thermal conductivity. So the diamond takes all the heat away and keeps the electron beam from quickly melting the lead. And if you want to buy this lead diamond sandwich, it's the lead that costs much more than the diamond because it's isotopically enriched in lead-208. And so the diamond foil works for a while. Eventually the beam chews up the target. So we made 10 targets to do the experiment. And all these targets are cheap compared to the calcium-48 target that we used for CREX, but I'll get to that. The scattered electrons are collected in two 5-story high spectrometers. And then all these beam monitors are crucial for controlling holistically correlated beam properties. When you flip the spin of the electron, you want nothing else to change. The energy of the electron or the position of the electron has to be controlled to very, very high precision to control the systematic errors. So decades worth of work went into learning how to control those systematic errors. Okay. And I guess I should say it's about a month of actual beam time running to get the statistics and roughly 2 or 3 months of real time or pack time that got charged. It's actually more than that. Any rate, that's the scale of the beam time. Okay. So the measured parity violating asymmetry is 550 parts per billion. So half a part per million, 10 to the minus 6. There's the statistical error. Well, actually, it's the sum of statistics and systematics, but it was dominated by statistics. Okay, so this is what's measured. That's the parity violating asymmetry, the difference in cross sections for right or left-handed electrons. A whole series of models is one way to do this. So if you take a model and calculate its weak form factor and its charge form factor, well, actually we include Coulomb distortion. So we calculate the cross section by summing over partial waves. But never mind, you can predict the parity violating asymmetry given a bunch of density functional models. And then for the models which reproduce the asymmetry, they have weak radii around 5.8. So the measured weak radius is 5.80 plus or minus 0.075 Fermis. So that's the main experimental. Okay, and you can subtract the charge radius is 5.5. So 5.8 minus 5.5 is 0.3. So that would be the weak skin. If you take out the form factors, the neutron skin is 0.28 plus or minus 0.071. So the neutrons stick out in lead by a little more than 0.2 fermis.
So Rn and Rp are the point nucleon
Radii.
RMS radii, is that?
Yeah.
right? Yeah.
That's right. So each is about 5.5 fermis. And PREX was at a momentum transfer of about 0.4 inverse fermis. So it's a low momentum transfer because lead is big. And so we had to run at 1 GeV, which made us very unpopular at Jefferson Lab because that was a really low energy that nobody else wanted. Okay, so that's the experimental result. And from that parity violating asymmetry, I'll talk about this in a second. If you fit a 2-parameter Fermi function for the weak charge density, this is what you get. So this is the extracted weak charge density. The area under this curve is the weak charge of lead. The error bar here is the dominated by the experimental error in the parity violating asymmetry. And there's the experimental charge radius, and now here, this is our measurement for the weak radius, and that's our error in the weak radius. Okay. Here's the experimental charge density. So the solid red is actually the experimental charge density. And you can see the shell oscillations. There's this 3s proton gives you this little bump in the middle, but it's really small. So we actually have measured the shell structure for the charge in lead. We haven't done that with the weak. That requires experiments at high momentum transfers, which are essentially impossible for the weak interactions. So we can't measure these little shell oscillations, but we can determine this average density. So the average internal weak charge density is here. The average charge density is this dotted line there. And then you can just add these two. This is essentially the neutrons. And so here's our measurement of the interior baryon density in lead. Okay, so now we can say something about nuclear saturation. Here's our measured baryon density in lead. It's about 0.15 nucleons per cubic Fermi. And this is the nearest clean, direct observable to nuclear density. Okay. This error bar here is not in lead. That's infinite nuclear matter. So this is chiral EFT calculations of the saturation density of infinite nuclear matter. So binding energy is a function of density. So you look at this red curve, and there's where its minimum is. N3LO is one higher order in the chiral expansion than N2LO. So the blue is a low order calculation, and the red is one higher order. And this shaded red there, that's their prediction of their error bar for nuclear saturation. And so if you project this down on the density axis, you get that black error bar. Okay, so this is infinite nuclear matter. And it's close to what we've observed in lead. Now, you could try and extrapolate. One of the reasons this lead differs from infinite nuclear matter is you have surface tension. So the finite surface tension tends to pull lead in and make the finite nucleus density higher. But then you also have Coulomb in lead, which pushes the nucleons out. So surface tension and Coulomb tend to cancel. And so we expect the interior baryon density in a heavy nucleus to actually be pretty close to the saturation density of nuclear matter. So now we have this direct measurement of the baryon density. So this is a direct measurement, if you like, of nuclear density. Great. So just a couple words about this two parameter. Actually, let me leave it there. So here's our measurement of the baryon density, the interior baryon density in lead, 0.15 plus or minus 0.004. So we've measured this baryon density to 2.6%. And it's, for the average density in lead, it's, I would argue, model independent. Okay, great. So we've determined nuclear density. Why does nuclear matter saturate at that density? That's complicated and subtle. We said 3 nucleon forces are important. There's a complicated interplay, the tensor part of the 2 nucleon force and their repulsive forces. So observing 0.16, or what we observed with 0.15 nucleons per cubic Fermi is non-trivial how it got there. Great. It's not just the size of nucleons. Okay? But the size of nucleons, there's maybe another scale in the problem. And if you had a way of squeezing nuclear matter to even higher densities, at some point you might find this scale where the cores actually touched. And then nuclear matter could become really strongly repulsive. And if you like, the cores may be the reason we can support 2 solar mass neutron stars. We observe very massive neutron stars, and they're held up against gravity, and maybe it's these strong core, repulsive cores that's holding them up. Okay, but I'm getting ahead of myself. Let's go from lead to neutron stars. Okay. The pressure of neutron matter. So lead-208 has 44 more neutrons than protons. Those extra neutrons, the pressure of that neutron-rich matter pushes them out against surface tension. If it's a high pressure, you'll get a big neutron radius. So this Rn minus Rp that we've measured, that's strongly correlated with the pressure of neutron matter. The thicker the skin, the higher the pressure. Okay? If you want to measure pressure, pressure is force per area. And the way you measure a force is with a spring and a ruler. And PREX is the ruler that measured how much the spring was stretched, that Rn was bigger than Rp. Okay, so we're essentially almost directly measuring the pressure of this neutron-rich matter in the skin of lead. Okay? And now these are not to scale. A neutron star is 18 orders of magnitude larger than lead, but they both involve neutron-rich matter at similar densities, I'll talk about that, with the same strong interactions the same equation of state pressure as a function of density of neutron-rich matter. So the pressure here has a lot to say about the pressure there, and the pressure is holding up a neutron star against gravity. So a high pressure gives a big radius to the neutron star and a thick skin to lead. Okay, so that's the idea. So let's give this little 2x2 chart. You want to measure the radius of a hadron. PREX and CREX measure the neutron radii of lead and calcium. NICER is an X-ray telescope, talk about that in just a little bit, that measures the neutron radius of a neutron star. You could also think about the polarizability. If you scatter two nuclei off of each other at large distances, the Coulomb interaction from one can Coulomb excite the other, and you can extract the polarizability, how soft and squishy the protons are in an atomic nucleus. Okay? So that's the measurement in nuclei. If you scatter two neutron stars off of each other, then the gravitational field from one tidally excites the other. And that allows you to measure the quadrupole mass polarizability of a neutron star. And the gravitational wave community calls that the gravitational deformability. So this is the measurement of a neutron star of the polarizability. Okay, so I want to talk about PREX and CREX, the radius of nuclei, talk a little bit NICER measuring the radius of a neutron star, and then LIGO measuring the deformability of a neutron star. And all of these have the equation of state in common. Okay. You tidally distort, so the gravitational field of one neutron star is deforming this guy. One way to think about it, you start in the spherical ground state. We have a quadrupole operator to a deformed excited state. That matrix element squared goes like R squared squared. So this goes like the size of a neutron star to the fourth power. The energy denominator, you sum over all the excited states. That energy denominator for gravitational system goes like 1 over the size. So it's R to the fourth over 1 over R. So the deformability scales like R to the fifth, just like the polarizability scales like R cubed. So the polarizability of an atom is a volume. And now we have this quadrupole quantity, which goes like the radius of a neutron star to the fifth power. Okay, great. So in 2017, LIGO observed the merger of two neutron stars and determined set a limit on the deformability. So this axis is the deformability of a neutron star, a 1.4 solar mass neutron star. This is the radius of a neutron star in kilometers. Neutron stars of order 12 kilometers. And here's the neutron skin in lead. So this is the neutron radius minus the proton radius of lead-208. Okay? These blue dots are a series of density functionals. The density functional allows us to solve for the structure of lead, but the density functional also implies an equation of state, and so we can calculate the radius and deformability of a neutron star. So a functional gives all three of these numbers. the observed deformability is the upper limit from LIGO is around 600. So the deformability has to basically be below this dashed line. So that's what LIGO observed. And now these blue dots show that the deformability goes like the fourth or fifth power of the radius. So this blue curve is actually 5.3 or something like that of the radius. Okay.
And the 1.4 signifies the mass of the neutron star?
That's right.
In solar units?
Yeah.
Okay.
And the LIGO very accurately measured the combination of masses,
The combination.
there's some uncertainty in the mass ratio, but it's fully consistent with.
So the sum of the
Close.
two masses was 1.4.
Well, 2.8.
Oh, okay, so it's half.
Yeah.
Okay.
Yeah, and this is chirp mass is what they actually measured, which is like the geometric mean of the reduced mass and the total mass. Okay. So if you compare the LIGO result to these density functionals, you see that LIGO implied that the neutron star radius is less than about 13 kilometers. If it's bigger than 13, then the star would be too big and soft and squishy. Okay, so the LIGO is to the left and below the dash line. Great. So that's gravitational waves. The X-rays, NICER is an X-ray telescope. It's on the International Space Station. And what it does is it's inferring the curvature of space near the surface of a neutron star. So if a neutron star has a hot spot, if that hot spot is on the near face, you see it. If it's on the far face, you see part of it because the X-rays get bent around the neutron star. So the extent of the curvature of space near the neutron star. So as the star rotates, you get a light curve, and the depth of the minimum in the light curve depends on the curvature of space. It's the curvature that's filling in the minimum, because when the hot spot is behind and you wouldn't see it in a Newtonian world, the curvature allows you to see it. So if the minimum is filled in a lot, then the curvature is big, and that implies a small neutron star. So that's how NICER measures neutron star radii. And so basically, for this particular pulsar, NICER measures 13, essentially plus or minus 1 kilometers. So this is the NICER range. So the X-ray observation say it's 13 plus or minus 1. The gravitational waves say it's 13 or less. And now we can put the PREX, the skin in lead is around 0.28 Fermis, that's the neutron minus proton radii. And so that, according to the density dependence of these functionals, suggests a slightly stiffer, higher pressure equation of state. And the simplest interpretation is 14 plus or minus 1 kilometers. So
14 plus or minus
1.
1.
Yeah.
Well, that's pure. Okay.
Yeah. So 14 plus or minus 1 and less than 13, there's some weak tension, and around 13 is consistent with it. So that's the results from 3 extraordinarily different ways of measuring the equation of state of dense neutron-rich matter. So PREX is probing the equation of state around nuclear density, and NICER and LIGO are probing at its most sensitive around twice nuclear density. So they're the higher density observables. Okay. Gosh, well, we have a second measurement on calcium-48, and how are we doing on time? I don't mean to.
It's fine.
So let me just say a little bit. So chiral effective field theory, these three nucleon, in particular, three neutron forces that increase the thickness of the skin and raise the pressure of neutron matter. So CREX is measuring the neutron skin in calcium-48. That's a lighter system. You can more directly compare it with microscopic calculations and with chiral effective field theory. Forces, PREX, the measurement on lead, is better for inferring the pressure of neutron matter and comparing to the neutron star. Okay, we worked really hard to control the systematic errors. So I'm not doing the experimentalists, the 100+ people in the CREX collaboration justice. They worked really hard. We really believe that systematic errors for this difficult measurement are much less. So statistical errors here, the systematic errors are significantly smaller. Okay, and one way to give the CREX results is the charge form factor minus the weak form factor. So this is the Fourier transform of the weak density. Calcium-48 has these 28 neutrons and 20 protons. So there's 8 extra neutrons in there. This difference in form factors at the momentum transfer of the experiment, which is 0.9 inverse Fermi's, that difference is 0.028 plus or minus 0.005. So we can just plot the charge minus weak form factor. This is like Rn minus Rp, but at the experiment it's at higher Q squared. So this is less model dependent. And this is charge minus weak for PREX. We could equally have plotted the neutron radius minus the proton radius. Okay, so there's the PREX for the skin of lead. Here's CREX for the skin of calcium. And then here are a whole bunch. The black is this crazy big family of relativistic mean field interactions with an incredibly small symmetry energy. So the density dependence of the symmetry energy here is actually negative, which is crazy. And then here, this density dependence is large and positive. So this is very low pressure, and this is very high pressure for neutron-rich matter. And then these are non-relativistic density functionals, just basically a random sampling of a bunch of them. And so PREX has a thick skin. Calcium, we're finding a significantly thinner skin in calcium-48. And theory doesn't directly get here, but at the 90% confidence level, there are a number of calculations which are consistent with both PREX and CREX. Okay, and so let me skip all these. MREX is a proposed experiment at Mainz to measure the neutron skin in lead more accurately than PREX. So this is the follow-on to PREX. And so Brendan Reed is a student working with me, has done tremendous amount interpretation of PREX and CREX, Farouk Fatoyev, Jorge Pikarevich, and the large experimental cast, and certainly don't mistake me for an experimentalist. I thank you very much.
Is there any questions?
I have a question. If you go back to the PREX global comparison with different experiments, it was in the lower left-hand corner, the claim LIGO preferred, favored, I guess is the word.
Yeah.
Rated. Where did that come from?
So LIGO measures the deformability. The deformability scales the radius of a neutron star to the 5th power. So these density functionals, we can calculate the deformability and we can calculate a radius.
Okay.
So if you compare the LIGO observed to our blue curve, then you can set a limit on radius.
When you use these equations of state, is that assuming homogeneity of the neutron star, which is?
At high density, yes, and there's no phase transitions. So there's no quark matter.
And there's, what about at low density though? Is there?
Yeah, so there is a crust
There is a crust in these equations of state?
because the radius depends a little bit on what you do
Yeah,
with the crust.
right.
So it's not that you're measuring the crust, it's just that you have to put a realistic crust on.
So these
to-
dots all represent doing something special at the crust, which is,
Yeah.
Okay, so are you worried that all of the theoretical points are so far away from what would be considered kind of the best overlap region, which is in this lower left-hand area? There's hardly any equations of state that.
Yeah,
are
so
down
let
in the
me-
lower part there.
so we thought about it a lot more here. And so here, and that was one of the things Brendan Reed, my student, did, is these relativistic mean field interactions are crazy compared to most of them out there in the literature. These have really small skins. And so he generated them just to make sure we had a big enough range to compare against.
And hard versus soft equations of state, where do they fall on?
So hard is up here, soft is down there. The higher the pressure, the bigger F charge minus F weak or Rn minus Rp.
Mhm. Is there any way of putting supernovas information into the picture?
So supernovae may or may not depend on the equation of state. There's lots going on in a supernova. One way to do it that I like is measure the total energy in neutrinos. And that's the binding energy of the neutron star.
Of the neutrons?
Star that you make.
Oh, okay.
So in the ideal world, you'd have some way to measure its mass, and then you measure the binding energy, and that's a really unique measurement. And that would essentially tell you the radius. Or equivalently, if you get a small binding energy, the neutron star you made was either crazy light or crazy big, or some of the energy went into axions or some dark matter thing.
Is there any control? I'm sorry for all my questions.
Oh.
Any control on your what you keep and what you don't keep in the individual points here in terms of the maximum neutron star mass condition?
Oh, so we've taken a bunch of different mean field or density functionals, simplest way to say it. Some of those functionals have been chosen to make sure you have two solar mass neutron stars. Some, yeah,
but not all.
that's right. And these really soft guys down here, it's really hard to make a two solar mass neutron star if it's that soft.
Right, so if you put the condition on that you only keep the ones that obey that condition.
Yeah. It's a little bit model dependent. If you made the equation of state suddenly turn much stiffer at beyond nuclear density, then you can
Why is it important to use double magic nuclei as opposed to neutron-rich even nuclei?
So there's an experimental reason and a theory reason. The experimental reason is doubly magic have high first excited states. So you have to isolate the excited states from the ground state. You want to measure the parity violating asymmetry of the ground state. So if you have a low first excited state, you need really big energy resolution, good energy resolution. And that basically costs count rate. You have to work hard to get that. The theory reason is doubly magic are the simplest nuclei, which may be closest to infinite nuclear matter. We're interested in the pressure infinite nuclear matter. We're not interested in the deformation of uranium or some special nuclear structure effect for the individual nucleus.
So what's your thought on why there are no candidate equations of state that seem to be consistent with CREX and PREX? So yeah, that's a 67% level. So.
Yeah, these are what we got, and so this is with the form factors. It's slightly more model dependent, but it's easier to say if now we have the neutron minus proton radius. So there's some model dependence to this CREX point.
But still,
The coupled cluster calculations, the Oak Ridge group, they've now done coupled cluster calculations for lead. And so you have to be careful. These error bars are actually pretty correlated. So I really should have drawn this diagonal or something. But nevertheless, this is more or less consistent. It's consistent with CREX with the upper end, and it's just below the lower end of the PREX. So this region here is certainly favored by the most number of theoretical calculations. And now is PREX just a statistical fluctuation, or is it really telling you that the pressure may be a little bit higher than you expected? And so we really would like to reduce this error, make a better measurement of PREX. And that's the motivation for this MREX at Mainz.
DOM stands for, sorry.
Oh, so this is Wim Dickoff, it's the dispersive optical model.
Right.
And
First of all,
it predicted or was in very good agreement with PREX, but it then went and predicted a calcium 48 skin, which is much bigger than what we measured.
So just a comment that assuming that you do the equation state that actually has a dark matter inside, should it increase the pressure for that and goes closer to the PREX regime, right?
So I mean, quark matter happens presumably at higher densities.
Yes.
So if we're looking at finite nuclei, it doesn't show up here, but it could have showed up in this comparison.
Mhm.
That the nicer and LIGO, those measurements are at high density, and PREX is at low density. So one of the ways to explain why LIGO is a little bit lower than PREX is there's a phase transition that makes it softer. I would say that's a little bit of extreme interpretation based on the measurements we now have, but that's why we want to do this comparison. Because if they don't agree, then it's suggesting a very interesting density.
Is there any other question? Any question on Zoom? Well, if there is no more question, I think, thanks again to the speaker.